Hello and welcome to my channel. For this video, I would like to show you a very useful piece of code in machine language and how I was able to use it to enhance a program for geography class. In geography class, we were given a program that simulated municipality zoning. For example, will you make one block education oriented, another commercial, another for retail, another for housing, and so on. So before we go too far, I want to make it clear that I do not have that program. I made a conscious decision as a student to not retain a copy of that program. It didn't belong to me, and I wanted to respect the works of the teachers and whoever else was responsible for that program. So what you're seeing instead is a mock-up, just something that takes time to draw a screen. This is based on the one-line maze draw algorithm that you've seen on YouTube from other channels. This is just another variation of it, and I did this just to demonstrate how long it takes to draw a screen when you don't have optimizations. So getting back to my geography class story, once the main screen got drawn, we would have a secondary screen where we could put some inputs which would affect the original screen. But once we did those inputs and returned to the main screen, it would have to redraw everything all over again. This was very inefficient, and I could spot a problem right there. BASIC is very good for a lot of things, but sometimes it needs a bit of help from machine language to perform a simple task. And the simple task that I could see with this was I need to make a copy of that screen, dump it somewhere in memory, and then return it when we go back to the main screen. And if you use your imagination in that, you could probably find use cases for this very scenario where you just want to copy the screen, put it somewhere else. Maybe you want to examine it, maybe you want to restore it, or whatever. I proposed the solution to the teacher and said I'd just like to take the software home and work on this a bit. The teacher obliged me, so I did. I came up with some machine language, found the hooks in the program where it needed to do a snapshot and where it could do a restore. And then I presented it back to the teacher, back to the class, and we were all good. So here is the modified version of the program, but now it has some machine language as an advantage to it. And once it finishes drawing here, we will see exactly how that manifests. So we're just about done. I'm going to go to the other screen. We'll take a snapshot. We took a snapshot. Return. Okay, the snapshot has been restored. Instantaneously, we got our screen back. Okay, so now that we've seen it in play, let's see how we can code it. So I made a loader program in BASIC, and I'm going to approach this a slightly different. I'm not going to just give you a big data dump. I'm going to show you the code line by line, what the machine language is compared to its data statements. The reason for this is that you may be able to adjust this for your own purposes. If you have different memory locations that you want to copy, you could conceivably construct your own code from this without ever going into the machine language monitor. So the first thing we see is the starting address. I chose C000 hexadecimal or 49152 for the snapshot. And on line 20, the R is the restore command, which is 56 bytes into the code. we have a typical for next loop to load everything into memory, and then we will print the output giving you the instructions. Okay, so sys49152 to snapshot, sys49208 to restore. Those are the commands that I used in that previous program, that mock program. Okay, so there, we've stored the screen and we've recovered it. And now let's break down that machine language in its data statements. I'll show you the first section. This is the snapshot section. And we create an index out of Y. Now normally we would, if we were copying memory, we would just use all 256 bytes of every page. But in screen memory, we're only dealing with 1,000 bytes, not 1,024 bytes. So we can only go up to 250 in this case, which is why I've had to break it down into portions of pages. This is not optimal, but it is accurate. This code is also quote unquote unrolled. It is more explicitly stated here rather than an elegant piece of code, because this will reduce the number of tests involved and the number of extra CPU cycles required to go through the loop. I've also made it explicit because you may want to alter these addresses if you've altered where screen memory is. Color memory is always going to be a D800 hexadecimal, but your screen memory, the power on default, will always be at 400 hexadecimal or 1024. So 99% of the cases, this code will work perfectly fine for you. So it's my belief that if you study this long enough, you should be able to hack it, reverse engineer it, make it your own. The only part that I think might trip you up is this branch not equal statement at the end of the test, because it is relative to the code. So it goes forward or it goes backwards. In this case, it goes backwards like 52 bytes or so. That's why you see a 203 on that line. So if we know what the snapshot code looks like, we can take a look at the restore code. And it's practically the same as the snapshot, but just in reverse. All the addresses have been reversed because this is a copy from the staged memory back to the original screen memory. So if you've been watching and looking for patterns, you may have noticed that the first number on each data statement is the command in machine language, and then the second and third numbers on each line are the values. They are in reverse order, so like we're looking at the 5th page here, so 5 is the third number, not the second number. These days, we all have spreadsheets at our disposal, and a spreadsheet is how I convert machine language back to data statements using cells that convert hexadecimal numbers into decimal. So that's the video. I hope this was useful, and I hope you stick around for the channel because I've got other stories to tell. I found this story particularly interesting because I don't have the original programs, but I didn't need the original programs. All I needed to know was that I knew how it was done, and I could always recreate it on the fly. So I tried to find an interesting way to present it, but I do realize that despite my efforts, this is kind of dry, and I'm not the most dynamic or entertaining person. Bye for now.